Hey, folks. For this discussion, we're going to talk about moment of inertia. And let me start with okay, so for linear motion, if I ask you what is mass, okay, there's two ways to answer that. One way is to say mass is the amount of stuff you're made of, kilograms, right? And if you go to the moon, that doesn't change. But in a motion sense, mass is an object's resistance to acceleration. Okay. So if I throw a tennis ball and a bowling ball towards you at the same velocity, the bowling ball is going to be harder to stop because it's got more mass, it's got more inertia. Okay. Well, we have a similar thing in rotation. There is a resistance to angular acceleration, and we call that moment of inertia. And I'm going to kind of walk you through a couple different ways to calculate that. So the first thing I'm going to do is imagine that you have a circle and you have a rock that's traveling in that circle. Maybe it's attached to a string or something and you're twirling it over your head. And I just asked you to calculate the kinetic energy of the rock. So the kinetic energy would be 1 half mv squared. Let's say I didn't give you velocity. Let's say I gave you the omega and the r, and I said, in terms of those things, calculate the kinetic energy. Well, okay. So you would say 1 half m, and then v is r omega, and you'd square that. And you'd get the following. I'm going to group it a certain way. You get 1 half m r squared omega squared. The mr squared, that is our moment of inertia. Moment of inertia. Okay. The letter that we use for moment of inertia is a capital I. The units are, well, it's kilograms times meters per second, or sorry, kilograms times meters squared. Okay, that's our units. So if you notice in that equation, there's two things that are important. Not only is the mass of the object important, but how spread out it is. So for instance, if I took the same rock and moved it out here, okay, and gave it the same angular velocity, okay, its moment of inertia, well, if you're doubling r and you got to square that, its moment of inertia would be 4 times as much, which also means it would be 4 times as hard to stop it. Okay, so both are important, mass and distribution of the mass, but in this case, distribution is actually more important because it's r squared. Okay, now mr squared, we would say that would be the moment of inertia would be mr squared for a point mass. Okay, so if you have an object that's either a point mass or a series of point masses, you just add up the mr squared. So more formally, we say the moment of inertia is the sum of the mr squareds for objects. Okay, um, and r in that equation, by the way, is always measured from the axis of rotation. Okay, and we'll do some examples with that, so it kind of makes sense. So like an example of this, imagine you have a bar and then you put two weights on it, and you put the weights here and here, and you stick your hand there and you try to twist it back and forth. Okay, so you're twisting it, clockwise, counterclockwise, back and forth, and you're trying to change the clockwise to counterclockwise, back and forth as rapidly as you can. Okay, if I take that same bar and I move those weights to the end, okay, the same weight, same bar, and say same thing, you know, shake it back and forth or rotate it back and forth rapidly. The second example, that's going to be harder to do. It's going to be harder because even though you have the same amount of mass, it's more spread out. The radius is bigger. Okay. Another example of that would be like a door. So imagine you have a door and it's got a couple hinges. So here's the two hinges. Okay. And there's a doorknob. So you go to pressing the door to open it. Okay. What if I took that same door and mounted it like this and put the two hinges like that and put the handle, let's say, somewhere over here? Okay, this door would be a little harder to open because it's more spread out now, even though it's the same mass. Okay. Now, if we go back to our kinetic energy equation, another way to write kinetic energy, and this would be kinetic energy rotational now. It's 1 half, well, instead of saying mr squared, we just say I for moment of inertia, and then omega squared. So that's kinetic energy rotational, which we'll do a lot more of in subsequent chapters. But for now, you should at least be familiar with the equation. Now, for calculating moments of inertia, so I'll start with a point mass or point masses. So let's say I've got the following object. It's a cross, all right, like so. And let's say that those are really thin, light metal rods whose masses we're going to pretty much ignore here. And I stick some masses on the end of each thing. So let's do a 2m there, an m there, an m over there, and a 2m down here. Okay. And I ask you for the moment of inertia of this 4-mass system. Okay. Well, right now, you can't answer that question because I'm not telling you how I'm spinning it. How I'm spinning it makes all the difference in the world. Okay. So here's what we're going to do. Okay. And I'm going to, by the way, I'm going to number these 1, 2, 3, and 4. Okay. So we're going to spin it. The first time we spin it, we're going to spin it about this axis that I'm drawing. We'll call that axis A. So like mass number 1, it would be like coming out of the page at us. And mass number 3 over there would be going into the page. Okay. So that's how we're going to spin it when we do A. Then we'll do B. This will be axis B. And so in this case, like the top mass, the number 2 there, maybe he's coming out of the page at us. And the bottom mass, 4, is going into the page away from us. Then we're going to do C, which is going to come in and out of the page there. So imagine this whole thing is going counterclockwise around that point. That's going to be our axis C. Okay. And then axis D, I'll put here. Okay. And so now we're going to spin this such that A is coming out of the page at us. And then, I'm sorry, the bottom mass, the 4, is coming out of the page at us. And the other 3, 1, 2, and 3, are going into the page at this moment. So that's how we're spinning it that way. All right, now having said all that, we're going to calculate the moment of inertia of this object about those 4 axes. Now, by the way, as you think about this, which one would be the hardest to spin? Like in which orientation would it be the hardest to spin? Now, I also have to give you some lengths here. So let's say from the center to the left mass is L, same with the center to the right, same with the center to the top, and same with the center to the bottom. And then just for fun, let's call this 1/2 L. So therefore, this would be 1/2 L, the total being L. Okay. All right. So the moment of inertia about point A. So I'm going to label that I sub A. Okay. That would be sum of the MR squareds. So I'm going to go in order by number. So if I'm spinning this about A, the radius is the perpendicular distance from the axis to the mass. Or another way to think of that is the shortest distance from the axis to the mass. So what is the distance from the A to number 1 there? Well, it's just L, okay? So we're going to have m times L squared plus for mass 2. Mass 2 is literally on the axis. Its distance from the axis is 0. So I'll put a 2m, but then it's 0. Okay. And then if I look at mass 3, it's an m, and it is also L away from our A axis. And then number 4 here is on the axis, so it's a 2m, but it's 0 distance. So those are going to be 0. And you simply get, if you add all these up, you get 2ml squared. So that's an indication of how hard it would be to spin around A. Okay. Now we'll do B. Okay, so I sub B is, okay, so if I look at B here, mass 1 is on axis B and mass 3 is on axis B. So they're going to be zeros for their distances. 2 and 4 are each L away from B. So what you're going to have here is you're going to have an m times a 0 squared plus a 2m times an L squared plus an m times a 0 squared plus a 2m times an L squared. And you're going to have 4 ml squareds when all is said and done. Okay, so that means trying to spin this thing about axis B would be twice as hard as spinning it about axis A. All right, let's try C. okay, for moment of inertia about point C, okay, well, now that axis is like coming out of the page at us, and all four masses are L away from that point. So this equation simply becomes m times L squared plus 2m times L squared plus m times L squared plus 2m times L squared. And if you add all that up, you get 6 ml squared. So far, that's the toughest way to spin this thing back and forth, that would give the most resistance to the motion. And finally, we got moment of inertia about axis D. Okay, so this is where you're holding it here, and you're taking these three masses up here, and they're going into the page, and this guy down here is coming out of the page. So in this case, if you look, mass 1 is a distance L over 2 from D. Look at the perpendicular distance. That is this distance here. Mass 2 is L plus a half L, so 3/2 L away. Mass 3 is L over 2 away. And mass 4 is L over 2 away from that axis. So what we get is the first M is L away from the axis. I'm sorry, L over 2, pardon me. L over 2. We got to square that. The 2m is 3/2 L, so 3L over 2 away. The other single m is L over 2 away. And then the bottom 2m is also L over 2 away. Don't forget to square those distances, like so. And we're going to have to add all these up. So here we get an m L squared over 4. Here we get a 9, that'd be 18 ml squared over 4. We have another single ml squared over 4, and then plus this becomes a 2 ml squared over 4. We can factor the ml squared over 4 out, and we end up with 1 plus 18 plus 1 plus 2, so 22. Okay, and if you reduce that, you could say 11 ml squared over 2, which would be 5.5 ml squared. So that's just a little easier than spinning it about axis C. All right. So it turns out that any object you can make into a bunch of point masses, you can just add up their ml squareds. In the next video, we'll talk about what if it's not a bunch of point masses. So that's our next video. So I hope that was helpful, and thank you very much.